All right, good afternoon, everybody. My name is Paul Lewis. I am the Vice President of Policy and Finance at the Eno Center for Transportation. Welcome to the webinar this afternoon entitled Automated Vehicle Safety, the Next Step for Safety Performance Benchmarks. As folks know, in April of this year, Eno released a paper called Beyond Speculation 2.0. This was our foundational work for public policy and the role of governments in regulating and investing in infrastructure for automated vehicles. And one of our key recommendations was that we need to create some kind of standard for safety for vehicle automation. Companies and organizations around the world are developing methods right now to test and demonstrate automated vehicle safety. Governments working with industry to develop these frameworks for testing and putting together benchmarks. One of those companies is Intel with their subsidiary Mobileye. They've developed an open mathematical model that formalizes safe AV decision making. This webinar and discussion is intended to launch a broader discussion using this as one of the examples throughout industry, academia, government on how to develop a safety model. So to present what Intel has put together is Jack Weiss. He is here on the phone with us. He is a senior principal engineer at Intel and the vice president of autonomous vehicle safety standards at Mobileye. He has a 20-year career at Intel, building a reputation as a change agent, and combines a unique blend of embedded product experience with a knack for software and systems that will hopefully accelerate the adoption of automated driving. Jack is the co-author of Design by Example, which is a software developer's guide to universal plug and play. He's an adjunct professor at Portland State University. He is the holder of 23 patents with dozens pending, and certainly an expert on this subject matter at hand. So without further ado, I'm going to turn it over to Jack, and he is going to launch into his presentation for the next 10 minutes or so. For folks on the webinar, if you have questions, please type your questions into the chat or the question functions on the GoToWebinar control panel. This is should be on your screen. I will be addressing your questions once Jack has finished with his presentation. So again, if you have questions either now or after his presentation, please type them into the control panel. So Jack, take it away.
Thank you very much, Paul, and hello to everyone. It's an honor to be here on this very important topic around the safety of automated vehicles, and I think Paul's introduction and the Eno Center's call and contribution to this topic is very valuable, and we're happy to be here and have an opportunity to participate in this discussion. So let's jump into it. So when we think about driving today as humans, it's something most of us do. Driving, as an activity is inherently risky. The safest human driver would be the one that never drives, just as the safest automated vehicle is probably the one that never leaves the garage. And so in this video here that's playing, if you're able to see it, you're seeing kind of a typical rush hour scenario. And we drive in environments like this on a daily basis. It looks quite chaotic if you look at it from above. This video was captured with a drone flying overhead. You have people negotiating for space. Not everybody's really obeying the rules in terms of the lane markings and things, and they're trying to wedge themselves in to get to where they want to go. And so it's an excellent illustration of how driving inherently is a balance between safety and efficiency. And oftentimes as human drivers, we make driving decisions that we certainly feel are safe, but are often very assertive maneuvers that sometimes carry an inherent amount of risk. But this balance between safety and efficiency that enables this negotiation in traffic scenarios like this is how humans drive today, and it's how our road networks operate, and it's why vehicular transportation is what it is in society. So the challenge then becomes, how do we translate this human kind of safety model, if you will, with this balance between safety and efficiency to automated vehicles. And that's what we're here to talk about today. So from an industry perspective, there's been a number of attempts to kind of define what does it mean for an automated vehicle to drive safely. The most common and longest running argument is a statistical argument, and that's this idea that a self-driving car should be statistically better than a human driver. And the most frequently kind of cited metric for this is vehicle miles traveled. And the problem with that is, in these two pictures here, I think as you can see, there's a clear difference. And so just because I've driven millions or billions of miles doesn't necessarily mean anything, because miles driven in a rural environment is very different than miles driven in a dense urban environment. And so how do you compare these miles? And are we talking about the best human driver, the worst human driver, an average human driver? So it's very difficult to compare apples to apples with statistical claims around things like miles driven or disengagements. And so that's why a number of folks, including our own Department of Transportation here in the US, has said, this metric, while interesting, is not sufficient, as an argument for safety. So if not sufficient, then what else do we have? Well, the second approach that's been proposed in industry is, let's just say, you know what? The automated vehicle only needs to strictly obey the rules of the road. And all we need to do is sort of digitize, if you will, our driver's manuals that we learned to get our driver's license, and somehow put that into the machine. And if the machine just follows all those rules, then we're going to be in good shape. Well, there's two problems with that. The first is this, and here's a scenario where two roads bisect. And in a moment, you're going to see an automated vehicle coming from the left, and then another, let's say it's a human-driven vehicle coming from the bottom. And so if the automated vehicle is following strictly the rules of the road, it knows there's a stop sign there, and so it should just travel right through this intersection. But in this case, what happened is that human driver perhaps didn't stop. So what should the automated vehicle do? Should it follow the rules of the road, continue through that intersection, crash into that car and say, well, I had right of way, I was following the rules of the road? Or should it, realize naturally, as we humans do, that just because you have right of the way doesn't mean you get to always keep it, and that there will be others that violate the rules of the road, and you need to be prepared for that. Also, I grew up in the state of Oregon, and in our driver's manual, there's a basic rule that says that you should drive at a speed appropriate for the conditions. And that might sound good for humans, but how would a machine interpret that? How do we make that specific for an automated vehicle to understand? And so that's part of the challenge of how human safety models for driving work today. A third option is we should just say, you know what, our goal should be, let's design these systems so that they avoid collisions at all costs. And if we have this as a top level goal, then this is going to be the best solution. There's a very unfortunate problem with this, and here's an everyday traffic scenario. 3-lane interstate or other kind of area. If the automated vehicle is that car in the middle, there's absolutely nothing it can do to avoid a collision at all costs. Well, I guess it could. It could just simply never travel on a 3-lane road and be in the middle lane. Well, that's not a very useful vehicle. So think about this scenario as a human driver. If you're stuck in traffic like this with cars all around you, there's nothing you can do, to ensure your own safety if cars around you are intent on running into you. So this safety goal also doesn't work. So the question then is, what do we do? How can we define a safety model for automated vehicles that's reasonable, practicable, machine interpretable, but also follows human concepts of common sense and conforms with our expectations on what automated vehicles should do? And so that question then is, how do we define safe driving? How do we formalize what it means for automated vehicles to drive safely? And so with that, I would like to share a video here that should show up shortly to introduce you to a concept that Intel and Mobileye have contributed to the industry as a starting point for this conversation to consider a different way of approaching this problem. So let's take a look.
Everyone agrees that autonomous vehicles are the future of mobility. But how can we be assured of their safety? Although we don't consciously think about it, humans follow a few basic principles to help us drive safely. For example, always maintain a sufficient distance from the vehicle ahead of you, or the right-of-way is given and not taken. However, these principles are subjective and open to interpretation. To provide true safety assurance for autonomous vehicle decision-making, we must first clearly define those principles. Only then will we be able to program an autonomous vehicle that will be smart enough to negotiate the road alongside unpredictable human drivers. In order to formalize human common sense, Mobileye has developed the responsibility-sensitive safety model. RSS is an open and transparent model that uses mathematical formulas for safe decision-making by defining what constitutes a dangerous situation, what caused it, and the proper response to the dangerous situation. By doing so, we can ensure that the autonomous vehicle will not initiate a dangerous situation, and also ensure that it responds appropriately when a dangerous situation is forced upon it by others. For example, while merging into traffic, the autonomous vehicles will cut in only with a minimal safe distance as defined by RSS. RSS builds upon these simple definitions of a dangerous situation by incorporating more complicated scenarios, such as junctions, limited sensing scenarios, and even unstructured roads. This allows us to gain full coverage of all possible scenarios in a multi-agent environment and clarify responsibility for collisions involving automated vehicles in the real world. These are just a few examples of how RSS is designed to mimic human judgment using mathematical definitions. At Mobileye, we believe that the challenge of providing verifiable safety assurance of automated vehicles is one the entire ecosystem must solve together. Therefore, we invite industry players and regulators to engage with RSS as a starting point for finding a true safety guarantee for autonomous vehicles. Join us in our journey to make safe autonomous driving a reality. Mobileye.
So in that video, we've introduced this concept. We've published this in a series of academic papers for the entire industry to see, benefit from, and talk with us about. RSS is a transparent, technology-neutral safety model, and it provides two important functions. It not only from a design standpoint provides a check on the decision-making capabilities of an automated vehicle to ensure that it's only making safe decisions, but it's also a technology neutral performance benchmark that regulators and others can use for the assessment of the safety of an automated vehicle. It works in three parts. First, we formalize what does it mean to drive safely. And first and foremost, it means defining a safety envelope around the vehicle, a space longitudinally and laterally around the vehicle that the goal of the automated vehicle is to maintain, just like we as human drivers do. So with that space defined, then we need to understand what constitutes a dangerous situation. When has risk been introduced into the situation so that we can then take a proper response to try to restore that safe state. So these simple steps defined with behavioral characteristics are meant to apply universally to any number of traffic scenarios. The rules are, do not hit someone from behind, do not cut in recklessly. We talked about right-of-way as given and not taken. Be careful where they might have occlusion or pedestrians, occluded by other vehicles and things with limited visibility. And then finally, certainly if you can avoid a crash without causing another, the automated vehicle should do so. And this is it. The idea is we're not enumerating tens of thousands of scenarios. These are behavioral characteristics that I think many of us would recognize in ourselves. When we drive safely, we're often adhering to these behavioral characteristics. And so we've done the same thing, but formalized these characteristics in a series of mathematical formulas and logical rules that can then be formally verified. So let's take a look at this one click down further. The first thing first, as we said, define the safety envelope latitudinally and longitudinally. The second, you have an artificial intelligence-based decision maker in automated
Hey,
vehicles.
Jack.
Yep.
Hey, Jack. This is Paul at Eno. For some reason, the slides that you're going through are not showing up on the screen. Can you perhaps click back into those?
I'm sorry. My apologies. Thanks for letting me know that. Looks like when we switched over to the video, we lost the slides. Okay, is it back again? My apologies, everyone.
Yes, we can see it.
Okay, thank you. Apologies for that. So in this picture here, we see the safety envelope on the right-hand side, and on the left-hand side, you see the flow. Traditionally, this is called a doer-checker architecture. It's very common in robotic systems. And so you have an artificial intelligence-based planner that's recommending decisions for the automated vehicle to take. RSS acts as a checker and determines, is this a safe action according to the safety model? If it is, let's proceed with actuation. And if something else has happened, such as you're in danger, somebody cuts in recklessly, then we perform the proper response. And so in this model, from an architecture standpoint, this is how you can easily integrate this concept into any automated vehicle solution. As we said before, RSS is technology neutral. There is no special hardware requirement. There's no special product requirement. Anyone can easily implement these algorithms and add them to their system, and they're very low performance profile. So let's look at a simple example. So the first question is, what constitutes or determines a safe distance if you're following another vehicle? And the concept is based on simply, if the car that I'm following were to brake, how much space do you need for you to avoid hitting it? And that's based on physics, essentially. And so we have physical properties in the world, things like the velocity of each of the vehicles, the response time that it takes for the vehicle to notice the car in front of you is braking, and maximum braking capability of the vehicle in front, and the amount of braking I need to be able to stop. So these are all the parameters. So we parameterize these into a mathematical equation then that constitutes what our minimum distance is. So you don't need to understand the details, but this is all based on Newtonian physics. And so just like anything else in math and science can be formally verified and proven to be correct. And in the academic papers that we have published, we've included all the detailed proofs to these equations and more. So then we get back to that dangerous situation. And so if we have a longitudinal and lateral safe distance, we define a dangerous situation as when both of those are violated. And so in this case here, we are in a dangerous situation. So our time t is dangerous. And so if we're in a dangerous situation, then we need to perform a proper response, which is to brake and restore our safe distance. And so it's quite simple, and this is how you can see that it doesn't matter what kind of road we're on. We could be on a rural road, a highway, a gravel road, asphalt road, doesn't matter. The same concepts apply to any driving scenario. Here's another example about limited visibility. And so here we have a zebra crossing, and we know that, zebra crossings often have pedestrians, but right now the vehicle can't see any pedestrians because its view is occluded. And so the rules of RSS would include calculations on how should I adjust my speed, perhaps I adjust my lane position to be able to stop just in case a human were to enter into that crosswalk. So the question now is, does this work? And so we will try to switch to another video here shortly. And what I'm going to show you here is a video of one of our own vehicles driving around incorporating these principles. So there is no hard-coded scenario here. This is a natural environment. The real world is chaotic and unpredictable, and I think as you'll see, there's no way we could have thought of this scenario in advance. All we did was take the rules of RSS, apply it to the automated vehicle, and let it go. And so here is a video of that. So what you can see here, we've got a group of pedestrians trying to cross where there is no crosswalk. We've got cars coming around us. They're trying to get around us because we had slowed down for the pedestrians that were blocking our view. our vehicle is trying to maneuver for space. It's trying to see, hey, can anybody let us in? And as it tries to do that, we enter into the dangerous situation. So then we turn back in our lane and we try again and we try again. And then the kid runs in the front of the car at the last minute. And so the other rule triggered in once again. So a pretty crazy environment for an automated vehicle to be in, let alone a human driver. And so this is giving us confidence as we're trying this out in the real world that yes, in fact, this solution does appear to have promise. And so that's why we are happy to share these results and be implementing it ourselves. But what's the catch? You know, is this too good to be true? And there is an important part of this dialogue that we need to have with industry and government. And the catch comes down to, what are the reasonable assumptions that I can make about other users? So remember this formula, our minimum distance formula. There was a variable called Bmax, and Bmax is our assumed reasonable worst case braking of the vehicle we're following. And so just like as a human driver, you know, we have these things like 2-second rule, or in Europe, they take the speed in kilometers and divide it by half, and that gets you some sort of distance or something. But they're imprecise, you know, but this is a computer, so we need to be precise. And so we have to pick a value. So what should we assume is the maximum braking capability of that vehicle that we're following? And here's where it gets tricky, because different vehicles have different braking distances, and those different braking capabilities, and those different braking capabilities mean different stopping distances. So here's a chart with just a variety of vehicle brands. And you see, if we were following a Porsche 911, it has quite an impressive vehicle braking capability. This is in meters per second. Just by reference, an average automatic emergency braking system is around 1G, which is 9.8 meters per second. So that brand new Porsche does even better than most AEB systems. But a 96 Honda Civic there, quite a bit less, not surprisingly. So what should we assume? Should we assume every car is a race car and has incredible braking capability? Well, if we do, that means we're going to be maintaining very long following distances for every vehicle that we're following. And even if you were to accurately detect the vehicle type, how do you know someone hasn't made upgrades to that vehicle in an aftermarket standpoint? And so the challenge here is, if we always assume worst case, you're going to get a very safe automated vehicle, but you're going to get an automated vehicle that people don't want on the roads because it's following distance of 10 vehicles or something. So again, it's that balance between safety and efficiency. Another example is traffic violations. We would normally say that the automated vehicle, of course, should never break traffic rules. But in human drivers, we do this all the time, you know, and it's safe to do so, and it's socially acceptable to do so. But how do we define when automated vehicles should be allowed to do this? Should they ever be allowed to do this? So that's another open question. The third is, what if there are objects in the road? Let's say there's trash, or something falls out of the back of a truck, or there's a disabled vehicle. Certainly when you have the space, the proper response, according to the 5th rule of RSS, is that you should take that safe, evasive maneuver. But what if you don't have the space? And what if you don't have a choice but to collide with that object? Again, should you cross this double yellow line? Should you violate a traffic rule to avoid this accident? What's the right way for automated vehicles to respond? You know, and safe driving is cultural, so the right answer may vary between country or geography. And so that's an important consideration as industry works with government to answer some of these hard questions. And then finally, pedestrians. Here's clearly, to a human, right, a residential neighborhood. And so there are no sidewalks in this neighborhood, as you can see. And so we should expect that humans that are in the road could at any moment kind of go in front of our car. So we need to drive very cautiously. Well, here's another example. And here we have sidewalks. And this is a very common road in the US, certainly. And the speed limit on these kinds of roads can be 35, 45 miles an hour. But if we as human drivers had to prepare for a pedestrian jumping in front of the road at any possible moment, we would never be able to drive 35 or 45, right? This would be a 20-mile-per-hour road. Yet we assume that because there's a sidewalk, the pedestrian's not going to do that. So again, what kinds of assumptions can we make to preserve traffic flow as humans do, but yet still be responsible when it comes to a safety standpoint. And so at the end of the day, RSS as a formal model for safety is a helpful tool to have this dialogue and help answer some of these important questions about what does it mean to drive safely? What are proper responses? And could that proper response vary by situation? What does it mean to be reasonably cautious? And does that definition change depending upon what city I'm driving in or what country the automated vehicle is operating in? These are key questions that we have to answer in a dialogue with industry, with government, with the public, for us to arrive at a safety model that can work for all. And then finally, as I mentioned, RSS can also provide an objective, technology-neutral performance benchmark to assess the performance of vehicles to the rules using the mathematical formulas to understand, is the vehicle driving safely according to the model or not? So at Intel, we believe this is a challenge much bigger than just us. That's why rather than keep this technology to ourselves, we've published it openly for everyone to look at and consider. We believe RSS is an excellent starting point to answer some of these hard questions. So we're engaging with industry, we're funding research all around the world. We have had a lot of wonderful conversations with government representatives, and we're eating our own dog food by deploying this in our own automated vehicle test fleet, learning from it, and publishing new results as we go along. So with that, I will say thank you very much for your time, and I'd be very happy to take questions. And my contact information is here on the slide as well, if anyone would like to send me a note directly. Thank you very much. Paul, back to you.
Great, fantastic, Jack. Thanks so much. That was really interesting, very insightful. We have a ton of questions, and I know that we try to limit these to half an hour. I think we're going to go over a few minutes to try to get to some of them. So if you do have a question, go ahead and ask it in the question function on your GoToWebinar panel. Again, I'm going to try to get to some of these. If we don't get to everything, we'll follow up with you afterward. But one question that comes up a couple times I've seen from folks is, you have a great base model, but you also have lots of unanswered questions, and you showed that on a couple slides back. Where is Intel and Mobileye, and I guess the industry, in answering some of those questions? What is the progress and the process to taking some of those questions and actually answering them?
Yeah, thank you. The first thing that we're doing to answer some of these hard questions is funding public research. So we have research that we funded in the US, at Arizona State University, at a number of universities in China, because China driving is very different than driving in the US, obviously, for those who have been there. And we're also funding research in Europe. And so one of the things that we're trying to understand, for example, the research project in Europe, in partnership with VTTI in the US, is to understand naturalistic driving behavior. So in other words, what would the parameters of the model be if it was a human driver? And that gives us a baseline that we can compare an automated vehicle to a human driver. So when we have these conversations about safety and we can say, well, here's what humans do today, how much would we like to dial up the safety for an automated vehicle, for example? So public research is certainly job number one, or not job number one, but the first thing that we're doing. The second thing we're doing is we're talking. We're having open and honest dialogues about the safety of automated vehicles. It's simply not possible to have no accidents anytime, anywhere. And so we need to be honest with governments about that. We need to talk with consumers about that. And we need to dig through some of these answers to understand what would we like these vehicles to do, and as citizens, and how would we like them to operate in the communities in which we live. And then once we arrive at a consensus answer across industry and with government, we can bake those answers into the model and improve it then for everyone to benefit. So those two things have been the primary way that we've been doing that, as well as, of course, implementing it in our own test vehicles.
Got it. So another question that comes up is, within your model, you talked about a couple different approaches, and one of those is following the rules of the road. Do we expect that automated vehicles are going to obey speed limits? And if so, how does that work in a driving environment where many drivers currently do not?
Yeah, our baseline position is yes, absolutely an automated vehicle must conform to all traffic rules and laws, whether it's a speed limit or it's do not cross a double yellow or whatever. But as the question proposes, and this is why that naturalistic driving baseline of how human drivers operate in different scenarios, how the question hints at is there's a lot of scenarios today where humans don't obey the rules of the road. And so, for example, let's do a traffic study to understand what is the impact of automated vehicles in a given environment that are strictly obeying the rules of the road in a mixed environment with humans that don't. Does that have a negative impact on road utilization? Does that have a negative input on throughput or traffic flow? And if so, then let's have a conversation. What should we do? Is there an allowance then in certain environments, certain roads where an automated vehicle, as wished for by society and government, that it should actually violate a traffic rule here because it's important to do so for other reasons. And so that's part of this dialogue. But clearly, from a baseline position, first and foremost, the automated vehicle must follow all rules of the road. Exceptions are an important conversation that we need to arrive at a consensus decision between industry and government.
Got it. So another question that's come up a couple times is infrastructure, where a couple of the examples that you showed had cities or roads that didn't have sidewalks, or that had both pedestrian traffic and high speeds, that had people walking in the street because there didn't appear to be good pedestrian infrastructure. What relationship does this kind of thinking, and maybe not the model per se, but thinking about safety also involve improving infrastructure to help avoid some of these conflicts and provide a viable and attractive alternative to folks to do something other than walk in the street?
Yeah, infrastructure can definitely play an important role in making the transportation network with automated vehicles more efficient. Things like cellular V2X could help provide hints and clues to an automated vehicle about what's coming. But at the end of the day, that infrastructure isn't going to be present and deployed overnight. It's going to take years, if not decades, for that to exist globally. And so any safety model for automated vehicle needs to work without depending upon infrastructure if we want them to scale and be able to operate in all areas, especially rural environments, not just urban cities, for example. So for everyone to benefit from this technology, we need a safety model that can work anywhere. But if infrastructure is present that provides useful help, whether it's a reserved lane for an automated vehicle or it's cellular V2X communication that's providing additional information from a smart city perspective, let's say, then great, let's use it, because that will make the system better and make the overall transportation network more efficient.
Got it. A couple questions about liability and responsibility insurance. Does this model take into account liability, and how is Intel Mobileye thinking about responsibility for any kind of crash?
Well, I think first and foremost, we need to figure out what does it mean for an automated vehicle to drive safely. It's certainly not the role of industry to assign responsibility or assign blame in accidents. That's has been and always will be the role of the authorities. And government institutions, insurance companies, sort of, et cetera. But generally, if we were to think about just human drivers, typically a human driver that's driving safely, based on a human definition of that, is not likely to be the driver that contributed to or caused an accident. Maybe it's still possible. So in the same way, if we have a formal definition of what it means to drive safely, hopefully that means the automated vehicle is very rarely the cause of an accident. And certainly if it was, then the existing legal and government bodies will determine that and take action appropriately. But first and foremost, let's figure out what it means to drive safely. And then with that, then I think the conversation about responsibility becomes easier, because now we have a definition of what it means to drive safely in the first place.
So you all rolled this model out several months ago. What's been the general reaction from governments, from industry, from stakeholders around the world?
Yeah, the reaction's been fantastic. We've really been overjoyed at how this has been received. We didn't quite know what to think, but we just thought, you know what, this problem is bigger than just us. I think this deserves a conversation, and this deserves collaboration in an open way with the rest of industry and with governments around the world. And so we've been pleased to receive thanks and support for trying to solve the hard problem. There's a lot of easy things to focus on today, and that work is important, and the industry is working on it. But if we don't solve the hard problem, like what we're talking about here today, about safety and what it means to drive safely, then all the easy problems in the world, if solved, still doesn't get you to wide-scale deployment of this valuable technology. And so we're really happy to have contributed to the dialogue there, and are encouraged by the response of others that we're building a coalition that's going to really try to solve the hardest problems that we have that could delay deployment of this life-saving technology.
Got it. And we're a little bit over time. I know that, and we haven't gotten to everyone's questions, but there's one that I want to get to, and kind of in closing, because I think it summarizes this pretty well, is I want you to talk a little bit about next steps, right? This is an interesting start. There's a lot of unanswered questions, and some of the most challenging questions that are still in front of us. How do we galvanize governments to really push for answering these questions? Who should be involved? How should that process work? And what are the next steps for answering these questions and creating an environment that can verify safety?
Sure. First and foremost, we would welcome anybody who wants to reach out to us. Again, my contact information is here. The more people that we can build as a coalition that want to cooperate together to solve this problem, I think the faster we'll accelerate a solution. We also think public research is a very important part of this, and especially dispersing that research internationally, because while this is an important problem, of course, for the US to solve, safe driving and safety is important in other countries around the world as well. And so that's why we've been funding a lot of that public research. The other thing that's important too is we really believe in industry standards. Again, this is a technology that's important enough to all of us, not just from industry, but just as consumers who want to benefit from this, that this really just begs for an industry standard. And so we're in the process of kicking off formal industry standardization efforts based on our original academic research here, so that the industry can benefit from standards that could be used internationally, so that anyone could implement this technology neutral technology in their vehicles. And so certainly myself and the rest of our team, we frequent conferences, policy discussions. We've got a global policy team with a presence in lots of different places. And so we would love to engage with any of you on this topic, because the more people, I think, talking about this and acknowledging that there are some hard questions here that we need to solve, the faster we're going to arrive at a solution that satisfies everyone.
That's great. Well, for everyone on the call, this concludes our webinar. We will be posting a recording of this conversation on our website, embedded in it, of course, the slides. Jack has graciously put his email address directly on this slide that you see in front of you. So if you have any questions that we didn't get to answer, you can either email us or him directly. Thank you all for participating, and we look forward to seeing you next time. And again, thank you, Jack, for your participation as well.
My thanks to the Inno Center for hosting this webinar. Thank you very much, Paul.
All right, thanks, and we'll see you all next time.